So, welcome back. Having seen both these tables, table 1 and table 2, and also understanding the basic references pressure and temperature with respect to table 1 and table 2, let us now go ahead and let us see a phase change process at constant pressure. With this we will be able to see two phases in equilibrium, liquid and vapor process in equilibrium. Also at the same time we will see how to read properties from the steam tables. What we had seen till now are only the first two columns from the steam table, but now let us have a look at different properties that one can gather from the steam table. So let us go back to our two-dimensional phase diagram, pressure temperature diagram and pressure volume diagram, and on these let us show a constant pressure process. So pressure being on the y-axis, any constant pressure process would look like a horizontal line in this diagram. So phase change at constant pressure would look like this, and I am showing for understanding sake this pressure is 0.10142 MPa, which is atmospheric pressure, and therefore this is where the water boils, and here I will go from L to V region, and therefore my LV saturation line comes into picture. So I may go from some L region, some point over here corresponding to temperature which will be less than 100 degrees centigrade, and then I will start heating it, and therefore the temperature will increase, and I would land up somewhere in vapor region or gas region depending on whatever temperature I want to achieve while heating the water and the vapor here. Similarly, if I show the same thing on a PV diagram, I get a horizontal line, but when I go from liquid to vapor, I pass hereby through a two-phase region, or I go through the dome, and in this dome what lies is liquid plus vapor two-phase mixture. Alright. So let us now show an animation of a process where we try to supply heat to water, and let us see what happens to this water. So what you see here now is a temperature volume diagram, because it is convenient to show on a temperature volume diagram when the pressure is maintained constant. So pressure here is 0.10142 MPa, and this is temperature, and 100 degrees centigrade is what is the boiling point of water at atmospheric pressure at 0.10142 MPa. And now here is my experimental setup. You can see here there is a small beaker, and I got water in this, which is shown by this blue tinged medium here, which is water, and I got something to heat this, some heat supply, some flame that will come over here, and this is water maintained at 1 atmosphere and 20 degrees centigrade. We know at this temperature and at this pressure the water is in liquid state, and this is the temperature, this is thermometer over here. Now what I want to do, because I want to have this process at constant pressure, I have maintained here something like a piston on this top, and when I go on supplying heat to this liquid, the pressure inside will increase, but in order to maintain that pressure constant, I will increase the volume over here. So when I increase the volume, the pressure, I will maintain the pressure as 1 atmosphere, and thereby I will say this phase change is happening at constant pressure. Having such a piston on this water, I will try to maintain this pressure equal to atmospheric pressure. Alright, now I will start this experiment, which is shown in the animation format over here, and because we start at 20 degrees centigrade 1 atmosphere, I will start something from this region which is in actually subcooled water region, alright, single phase subcooled water region. So let us start this experiment and have a look at what happens on a VT diagram or TV diagram. At the same time look at what is happening on the right side where the experiment is being carried out. So you can see this is my point 1, which is the initial position, and I have started heating this water. This is the flame that is coming over here, and you can see this water, right. Now you can see that it has reached point 2, and this is the phase change at constant temperature, which is 100 degrees centigrade, and you can see this piston is going up now in order to maintain the same pressure as 100 degrees centigrade. Now at point 4 there is a complete conversion of water to the vapor region, and I am going beyond that now, and I am heating it up to let us say 300 degrees centigrade, alright, and this is my final point which is at around 300 degrees centigrade approximately shown in this diagram. So what I have done, I have heated this water which was shown earlier in the blue color, went from subcooled liquid, went up to 100 degrees centigrade, which was heating of this water at constant pressure, and then at point 2 the phase transformation started at 100 degrees centigrade, wherein I had liquid plus vapor region staying together, they were in equilibrium, and this 100% liquid at point 2 became 100% vapor at point 4. During this phase change process from 2, 3, 4, the temperature remained constant. Of course, the pressure is always maintained constant here. And at point 4, suddenly temperature started increasing from 100 degrees centigrade up to 300 degrees centigrade, which is the point at 5. And this is what is a process would look like when I heat water. Heating is done at constant pressure. Alright, so this is what a phase change at constant pressure would look like as shown in this figure and in this experiment. Now I am showing here isothermal and isobaric lines. The isobaric line we have just seen that on temperature and volume diagram, TV diagram, and this was our isobaric process at atmospheric pressure. Same process is shown here on a PV diagram which comes as a horizontal line, isn't it, because the pressure is maintained constant. It goes from a single phase region to two phase region and then goes up to in a single phase region again. You can see one more constant pressure now. If I increase the pressure from let us say 1 atmosphere to 10 atmosphere, correspondingly again I can see atmospheric pressures being increased to some higher point, the boiling point will correspondingly change, and this is how the constant pressure lines would look on a TV diagram. What you see here also are the constant temperature lines. So isothermal lines would look on a PV diagram like this. You can see temperature remains constant and these lines go like this. Alright, so this is how the isothermal line would be seen on the PV diagram, and isobaric lines I have shown on a TV diagram. Thank you very much.